So I'm really delighted to tell you about my research interests, and which since my PhD were about adaptive assessment, but I got, so I'm gonna give you a brief idea about what I did. So I actually did a postdoc in Tokyo. So I lived in Asia a couple of years, and but before that I was more into, I didn't know which path I would choose between teaching or research. So in France, you have this kind of competitive exams in order to get a position to bring students from high school to higher education. And I was still hesitating between these two paths. So that's why there is a bit of overlap between the different things I did. And but the good news is that these days are more in France, you have an increasing focus on teaching computer science to a massive number of students. So that's why this kind of competitive exam also exists for computer science. So this is new. And so I'm quite involved in all this. So even if today I'm going to talk about machine learning in education, I also did, as Gauthier said, some competitive programming, and I was so much interested in it that I wrote a book about it with Christophe Dürr. And the nice thing is that all algorithms are available as open source, so you can see it's a Python package, a Python library that you can download, and all the code is on GitHub. So the main themes when we are talking about machine learning in education or AI in education in general, actually they revolve around this kind of themes, which are the fact that you want to focus on the privacy of students. You don't want their data to be used too much. Actually, it depends, because some machine learning works actually focus on detecting emotions in faces and see how this can be related to a dropout. And but this is not the research I will talk about, because I think mainly simple methods can be used to be efficient. You also have learning analytics, which is all about having some dashboards that can provide feedback to both teachers and learners. And what I'm most interested in is predicting student performance. So which means, based on learner data, how can you detect at-risk students or predict whether an exercise is too easy or too hard for someone. And also another focus that is also interesting for teachers is automatic grading or assistance to help grading a large number of students. And also how can we provide automatic generation of personalized feedback? So you can see this, for example, in programming, where someone is giving some code to solve a task, and they make a mistake, but based on the previous mistake in the past, systems are able to highlight the line that may contain an error to help people improve. And there is also such social network analysis, which is more interested in how a group may learn collectively. So this is the kind of research you will see in several communities. And to give you an example of what has been done, so this was presented at the Learning at Scale conference. It was a tool to help people grade, so that basically there is an AI system that will scan all the sheets of every student, and then they will take all the question ones and present them to the students so that they can over time refine their the grading. So for example, if there is a constant missing, so they will decide to remove 1 point or something like this. But this is actually used by these universities, mainly in the United States, and it help earn time in productivity, when you have many students. And indeed, this kind of grading becomes particularly challenging when you have millions of students in a MOOC and you want to be able to cluster like the similar answers from students, so that you can label a cluster and grade them at the same time. So as I said, there are several communities, and just to give you an example, so the idea is that from MOOC data, for example, you will try to devise ways to have some dashboards that will be given both to the students so that they can know where they are, like what are their weak points and strong points, and also for the teacher to have a way to assess whether like some students need further help. And so this is mainly done in the first two communities that are learning analytics and learning at scale. But also there is educational data mining, which is more interested in how you can model the learning path, the learning process of students. So which is more my expertise. So, and actually last year, this conference was held online. We hoped we could organize it in Paris. And there were 400 worldwide participants. We use GatherTown, and this community is mainly composed of people from the United States. And you can, if you're interested, you can have a look at the accepted papers. So this is mainly interested in models of learning, and more broadly, like artificial intelligence in education. So I also was interested, as Gauthier said, I was also interested in recommendation systems. So where you have access to some ratings of users grading, like rating items, which are movies, and you want to learn a representation of these users and items. So here on the right, you see that every orange point is an embedding of user, and every blue point is an embedding of manga. And you want to see what are manga that are close to each other, or users that are close to each other, so you can provide interesting recommendations for them. So it's a similar, we want to achieve a similar goal with students, but it's a bit more challenging because in this kind of platforms, you indeed have access to several people grading several items. But the grade is some information that you can trust. By default, you can trust that if someone gives 4 stars, it means that they like a movie. But if a student answers correctly a question, you're not completely sure that they understood the question correctly. Maybe they guessed the correct answer or something like this. So in knowledge tracing, which is the task that is popular in EDM, educational data mining, you have access to learning traces, which is the fact that student X answered correctly or not question Y, and you want to know what you can do with this kind of data. So a student can attempt multiple times the same question, and you want to detect which will be the moment when they will they will understand. So what can we do with this kind of data? Because actually, these kind of data sets are available. Some of them are available online. For example, at the Worcester Polytechnic Institute in the United States, there is an assessment data set with hundreds of thousands of learning samples. And you have also a Duolingo who likes to organize challenges at natural language processing venues, where they give you access to the outcomes of students, and you have to predict whether they will answer correctly, whether some new words will be too easy or too hard to type for them. So we can, from this kind of data set, we can compute the statistical difficulty of questions so that we can predict future performance of students and in turn personalize assessment. So I will be more into details later, but the idea about what you can do is the reason why I was interested in this kind of trees, when you want to adaptively, this is when you are killing this kind of who's it, where you try to make a decision tree to learn what is specific to this person, and we want to achieve a similar thing. And also, I was also interested in Akinator, which is like a genius that guesses. By asking you a question, they can guess who you are thinking about. Okay, so it's a 20 question, it's a 20Q system. But this is actually what we want to achieve for students, because at the beginning, you don't know anything about them. So you want to know where they are in the path. So to give you an idea about how to do this, let's assume that we have some task that is, let's assume you're a country and you want to certify the digital skills of your citizens. If you know that sending a mail requires the knowledge components, knowing what is a form or knowing what is a mail, and probably you can send a mail. And but a subtask of it is to be able to fill a form, and sharing a link requires the knowledge component that are being able to copy or knowing what is a URL, and so on. So if we ask task 1, okay, and people answer correctly, so probably knowledge components form and mail are mastered. So if I know, if I already asked task 1, I don't need to ask task 2, because it will give me a few information about their knowledge. So instead, we can administer task 4, and if they answer it incorrectly, so which means, as I know that already, this person masters what is a form, so maybe they don't know what is an URL, and so I can know what are the knowledge components that they don't master, and then I can provide them learning resources so that they can learn about it. Okay, so the idea is we want to do this kind of adaptive testing, and while being able to provide a feedback to the students. So what does it look like when it's discrete, like what I said? So you want to learn a subset of 0, 1 to the k. Okay, so there are 2 to the k possible knowledge states, and you want to learn these states by asking questions. So a natural idea is to ask the question that reduce the entropy of the possible learning paths, because the maximum entropy is when I don't know anything about the student. All the learning, all the knowledge states are equally probable. But then you want to cut this distribution in order to be able to be more certain about what is the knowledge state of the student. But the problem is that when k is really big, you cannot do this, because then you have the support of your probability distribution is too big, so you cannot do this. So you need to add some information. So for example, you can add a prerequisite graph about what are the knowledge components that you are trying to assess. And here, for example, I can only master independent and dependent events if I master introduction of compound events. So this is reducing the amount of possible knowledge states, and I can use it to have a lower complexity for assessing the knowledge of students. So there is so usually this kind of in private companies, usually this kind of prerequisite graphs are not available, but at the European Commission, you have access to this kind of curriculum of what someone should know about digital skills. So the European Commission developed this DigCamp curriculum that contains 5 domains. For example, information and data literacy. Am I able to search for information on the internet, for example? Or also communication collaboration. And you have also problem solving that may include some kind of programming. And also what is relevant to safety and digital content creation. But here you have 800 such knowledge components, which are also called skills. So again, you need a prerequisite graph to be able to assess them effectively. So in France, we actually, right after my PhD, I worked on applying what I did in research to this actual certification of digital skills that is today used in France for every citizen. So they collect millions of data. And when it was made, it was actually a startup funded by the government. Like it was a startup of the, we call it state startup from the French Ministry of Education. And at that time, we were only 7. So basically, like there are researchers who have to design 800 challenges, a couple of developers to develop the Node.js platform. And I was developing the adaptive assessment. And the good thing about this is that it's a free software. And you can also see it on GitHub. To give you an idea about what are the questions, for example, like they ask you in the French village of Mont-Trésor, what street is crossing Perrier Street? And like if you can answer correctly this question, maybe you know how to search information on the internet. So that's why you can get a skill that is of a certain level. And so the nice thing about this is it's not just a multiple choice question. It's actually some kind of challenge that whenever you will be able to solve it, you will get the corresponding skills. And there is some adaptive algorithm to find what is the best question to ask. And as you can see, there are different tests. This kind of adaptive algorithms will rely on some objective function that you have to optimize. So if the idea is to just know where you are in this whole graph of learning components, I just need to make a placement test. So that will assess your level adaptively, know your strong and weak points, and recommend you some learning resources. And this is low stake. But when you want to do an exam, like you want to certify, you are the French Ministry of Education, and you want to certify that this person has this knowledge, actually you just need to know a rough estimate. Like I don't need to know precisely what are the skills that you master. I just want to know that you're basically level 4 in safety and level 1 in digital content creation. And this objective will be slightly different. And something that is even more challenging, but that I'm interested in, is to see what are the questions that can make you learn faster. Like what is the next thing you should learn in order to have more knowledge. So like to go more efficiently into this diagram of this knowledge map. So the continuous adaptive assessments, like so far I just gave you an example of what you can do when you have a discrete knowledge state that you want to master. But when it's about level, actually there are many old research models, and this field is called psychometrics because it's related to psychology, to a psychological measurement of your latent state, the latent state of humans. And it was developed, I guess, like it's a bit related to IQ tests. And also, like the United States make a lot of money with this kind of tests that can, like the SAT scores and so on. But the idea with PICS in France is that we wanted to provide these tests for free. So the idea is that, like, let's say you have you want to model the probability of success of a student, okay, from 0 to 100%, given their level, which is actually continuous. So for example, if I have a student that is of level 3, actually they will have a 50% chance to answer correctly like a skill of level 3. And whenever it's, but if they are level 5, actually they have a higher probability, like 88% chance to get it correct. So these response model help us have a likelihood in a Bayesian meaning. So that I have my prior over, like maybe my students has, like I have some prior knowledge about where they can be. And given the fact that they answered correctly this question, I move my a posteriori estimate, like I can refine over time the possible levels they may be in. Okay, so, and then so that's how, using this kind of curves that are fitted on the learning traces I showed you before, I can learn what is the difficulty of questions. Because if I know that a student that is more proficient in this domain answered it correctly, maybe they can also answer correctly similar level, like, or easier level of questions. So what does it look like? So I assume that the outcome of a certain learner over a certain item is either right or wrong. Okay, it's a binary classification. And I want to learn two parameters, which are both the ability of all the users and the difficulty of all the items. I have a sigmoid as activation link, and the probability that they answer correctly depends on the difference between the learner ability and the difficulty of the item. So the idea is that we want to learn this kind of simple parameters for historical data. And then for a new examinee, when I have a new student, I just know already the difficulty of the items, and I want to know what is the ability of the students. So I want to ask an informative question with respect to where I think my student is, and I update the estimates of my student ability. Okay, so it looks like in practice. So first I ask a question of average difficulty, like a difficulty 0. And then, given this, if they answer it correctly, so this is the green dot, I will ask a harder question. If they answer correctly, I will keep increasing the difficulty. And if they make a mistake, I will ask an easier question. So this is how the adaptive tests are made today. So over time, I just refine my estimate on the difficulty of the ability of the learner by choosing adaptively the question that I will ask. So there is a problem with just doing this. It's that I let you think about what may be a problem about this. So the good news is that it's an optimal way to reduce the confidence interval, okay, and to converge quickly. So I don't need to ask 800 questions. I just ask 10 questions and I have a good estimate. But the drawback is that no matter your level, you will fail 50% of the time. Because if you're skilled, then you will have harder and harder questions until you reach the end. And even so no matter what, anyways, the system is adapted to provide you, to ask you the question that is more closer to 50% chance of answering correctly. So this is a problem because people feel bad at the end of the test, or they feel tired. So that's why you want to still adjust a bit this kind of hyperparameters. But so what we did in PICS actually is that you have this kind of 800 skills, but there are too many of them, and some of them belong to the same family. So that's why we designed a simple dependency graph between skills of different difficulty. And if the student answers correctly one node in the graph, then I assume that they can master what is easier than this skill. And if they fail at this node, then I can assume that they don't master what is at a higher level. Okay, so this is a way, and I want to maximize the number of validated node, which is a simple greedy objective, where so that I can make sure that I cover the space of possible possible skills in my curriculum. So this is what we used in production. So which is a bit playing between this kind of graph and which gives meaning, and also the Rasch model that I just described, which helps you filter among the same one line. But the thing is, we may not be just unidimensional. So for example, in language learning, you may want to, for example, with the Duolingo dataset, you may want to model the fact that someone may be typing on a device, like when they answer the question, if they're on computer or on smartphone, maybe they may not answer the same way. They may make different mistakes. And also, if they come from different countries, their difficulty may be different. So the thing is, so far we described the item response theory Rasch model that is just modeling two parameters, okay, the ability of the learners and the difficulty of the questions. But what we may want to do is to model multidimensional embeddings, okay, for both the user and the question. So here my user is represented by a vector, okay, with d parameters, and the difficulty, actually it becomes a discrimination parameter, which is an embedding for the question, plus a bias to say that maybe it may be a bit easier, okay, plus. So what does it look like? So you can represent. So for example, here I had a data set of 500 people answering 20 questions of fraction subtraction, just to illustrate. So here a black dot will be an exercise, and some of them are represented by spheres, okay, so that you can see what is the exercise. And the theta, which is the red parameter, is representing here. So suddenly it becomes similar to what I showed earlier really quickly with recommendation system. Here you have just two-dimensional embeddings. And you can see that if this person is here, then they may be positively correlated with the first axis and negatively correlated with the second axis. Okay, so the exercises that are in the same, that are correlated, are the exercises that will have a like if the exercises are correlated to the embedding of the student, then this parameter will be high, so the probability to answer correctly will be 1. But if they are negatively correlated, then the probability will be like this dot product will be negative, and then the probability will be 0. The estimated probability will be 0. So for this student, these two items are easy to solve, but this one is hard to solve. So you can see that when you have this kind of simple, like factor analysis, you can see that you have some exercises that discriminate only over one dimension, and they seem to not require to have the same denominator. And you have items that highly discriminate because they are far from the origin over both dimensions. So for example, this one and that one. And you can see that, for example, these two just require that you are able to put as the same denominator. So if I try to solve this fraction stupidly, I will do 3 times 8 minus 3 times 4, and I can make mistake when I do the multiplication. Okay, but I can also just solve it by doing 6 over 8 minus 3 over 8. So you can see that how from data only, like just the data of whether people got correct or incorrect the question, we can learn these meaningful parameters to be able to explain the difficulties of students. So first you have your prior over the knowledge. So in multidimensional ability, you have your prior, you don't know where is your student, but you ask a question, and given the fact that they answer correctly this question, you can have a new estimate of your student. So this is exactly what we want to be able to do. And this kind of, this is probabilistic inference. So you always keep some kind of resistance to just guessing by chance. So basically, like my student is in space, and I want to find the question that will help me see where they are in space most effectively. So how can we formalize this? Okay, so we want to maximize the likelihood of we want to find the parameters that maximize the likelihood. Okay, so which means usually you want to find you want to minimize the gradient. Okay, but the thing is the log likelihood. Okay, when you derivate it with respect to the parameter, okay, you have this nice property. But the thing is, what do we want to maximize? Actually, it's called the Fischer information, and it's the variance of this term. Okay, and it's how can I explain it easily? It's the fact that if this information will not surprise me, which means the variance of how I will move in space is high. Okay, so if it will not surprise me a lot, then it's a useless information. So if I already asked you to solve, you managed to solve a question of difficulty 3.5, then it's useless to ask you a question of difficulty 0.8. So this is really what you want to do. But the nice thing about this Fischer information framework is that it's a generic for any kind of response pattern. And then so that's why it's this is how you want to do it. And the little difficulty when you are in higher dimension is that this is a matrix. So you cannot maximize a matrix, right? You have to decide whether it's the volume or the trace of a matrix that you want to maximize, and all these criteria are stuff you can implement. But basically, what I want to do is to reduce. So, for example, another criteria I can use is to reduce the volume of the uncertainty that I have over where the student is. Okay, so that's why there are many index, many criteria that were developed in the psychometrics literature to do this. But if I go back to the unidimensional model I told you before, what does it look like? Okay, to ask the question with maximum Fischer information, I told you the probability is just a sigmoid of the difference between the student ability and the difficulty of a question. Okay, so this is my probability that my student will answer correctly this question. If I compute the derivative of the log likelihood, it's just this simple term, okay, thanks to the fact that the sigmoid is easy to differentiate. And if I take the second derivative, okay, it will be this term. And this term will be as high as possible when Pj is close, the probability to answer correctly is close to 1/2, 1/2, okay. So that's why what we want to do, intuitively, actually is what it belongs to this framework, okay. But as I said, this asking question of probability 1/2 is not what you would like to do to have a good user experience. So that's why Duolingo, for example, will use another term. And also, there are some, sometimes you want to do a compromise between, let's say you are in a higher dimension, and there are some dimensions that you know well. Okay, so you have a low confidence interval on these dimensions, but there are other dimensions that you would like to explore. So at each time you're hesitating between confirming your beliefs on one dimension or exploring new dimensions. So that's why other techniques were provided that are more related to bandit models. So that's why I encourage you to look at this kind of papers if you're interested, that are about multi-arm bandits in intelligent tutoring systems, or where's the reward, which is another nice paper where they show, like by Dorudi, where they show various learning objectives that can have an influence on the outcome. Okay, final thing I want to talk is I mentioned the fact that we would like to model a pairwise interaction with some extra information. So, for example, you know which countries the person belongs to, or like whether they are answering on a device. So I showed you how you can do logistic regression for Rash model is like a logistic regression for learning just one dimension. But the idea here is we would like to learn k dimensions, but also in order to model side information, such as the device used or some other information of context. So you can see that when you do IRT, you are basically measuring just one parameter for the students and one parameter for the exercises. In multidimensional IRT, you are similar to correlative filtering because you want to learn the correlation between the embedding of the user and the embedding of the item. But now I add a new piece of information, which is whether this person answered on mobile or on desktop. So how can I model it? I can say that I can introduce a new embedding to say that this term, for example, will be whether this user is proficient at mobile or not. And this other term will be whether this item is easy to answer on mobile or not, right? Like based on whether you're typing or something like this. So how does it look like graphically? Here you have you're modeling just one parameter, okay, for each user and one parameter for each item. You have a one hot vector for a user and one hot vector for an item. But a factorization machine will be a bit like this. So I have a one hot for my user, a one hot on my item, and one hot on whether it's a skill or whether it's like which device was used. And the expression of my response pattern, okay, will be given by some biases, and also the pairwise interaction, okay, between each pair of activated features in this model. So you can see that this can be seen as regression using sparse features, okay, because here I just have one hot vectors. So this is the expression of what it looks like. And we could show that actually when it makes sense to do this, even if it doesn't improve a lot the performance when you have too few data. Actually, the good news is that it's a more generic model than multidimensional item response theory, and you can use it for also trying to represent the embedding and visualize what are the where are your users in space, and what are the skills that they may be more proficient with. But the last thing is that learners evolve over time. So like whenever the really hard thing to measure in this kind of research is the fact that actually when you show students, you show items to students, they may learn over time. So they are moving in space, okay? And also they may forget over time. So these are actually assumptions that you can use to refine your model. But to give you an example with pics, okay, the question, people are allowed to use internet when they answer the questions. So of course, when they ask you like where are, like what is the name of this street that crosses this other street, it would be nice to know it by heart. Of course, it would be stupid. But the thing is, you may not know how to do it, but if you search on Google, you will learn how to do it. So that's why you were at some point in space, but you are at a new place, right? So the thing you want to do is to give more weight to recent samples than older samples. And we also developed a forgotten model related to what you would like to see in Enki systems, Enki-like system. You know, when you're, for example, learning kanji, and you want to know what is the kanji that will make the most sense for you to learn at some point in time. So for this, we developed exponentially decreasing model that may say that if this question was asked too long ago, maybe it makes time to ask it today. So you can have a look at the paper. It was published at the IDM conference. Okay, so now I will just give just a word about the title of this presentation, which is about information geometry. Actually, it was a term coined by Shunichi Amari, who was a Riken researcher, actually who is still alive and still makes amazing talks. And it's the fact that Fischer information defines the Riemannian metric on probability distribution. So you can see that the beauty of trying to adaptively assess the knowledge of students is related to like how much information in space, but I told you that information can be seen as the volume of uncertainty in space. And this is what is made in this research framework. Okay, so I will be happy to answer your questions now. Thank you for your attention.